Hello, welcome back. So in the previous lecture, we introduced the topic of a state space as another notation, if you will, or modeling approach to describe the dynamical systems through a specific structure and form. It was another notation next to the transfer function that we discussed before. So the first question that maybe we should address is how we can relate the two together. So that is the topic of this lecture, how we can go from a transfer function model to a state space model and vice versa. So in the systems that we usually deal with, before that, transfer function is only defined for linear time invariant systems. State space is more general, but for the topic of going from one way to another, obviously we need to only have linear time invariant system to be able to define a transfer function for it. So imagine I have a system, a dynamical system, a bunch of inputs and a bunch of outputs. The state space form very compactly can describe this multi-input, multi-output relationship, and within this system there are these internal workings of the state equations. But if we want to describe the same system with transfer function, we need to have individual transfer function, for instance, from y1, from u1 to y1, from u1 to y2, and all their combinations. In this cartoon example I have 3 inputs and 4 outputs. So to fully describe all the input-output relationship, I need to define 12 separate transfer functions. So let's start by going from state space to transfer function. That one is easier and more readily we can find answers to. And let's introduce a concept called transfer matrix, which is a matrix of transfer functions. Let's see how that works. So let me start from this equation. So x dot equals ax plus bu. This is a linear equation. And remember our good old friend Laplace. Laplace is also a linear operator or transformation. So I can take this equation and take Laplace of that. So going back to our notation, so I have s x of s, and this capital X is, draw it with maybe another color, is the Laplace of all these x's, x1, x2 to xn, all of them, function of s. So maybe I should have written it more explicitly. This one is in time domain, so this x is in time. X of t derivative equals a times x of t plus b u of t, and so on. And when I take Laplace transform, I take individual state variables to corresponding Laplace domain. So s x times s, and remember when we were talking about transfer functions, we always had 0 initial conditions just to extract the input-output relationship. So here we do the same, so ignore initial conditions. Ignoring initial conditions, so taking Laplace of x dot, I'm only left with s times x of s being a vector, equals a x of s. And I encourage you to expand this equation into multiple n linear equations, take the Laplace, and then convert it back to a matrix form to see how these work out. Plus b u of s. And remember, a and b are constant because we are dealing with linear time invariant systems to be able to define something like a transfer function for it. So I have x of s and x of s here. I can bring this one to the other side, and I will have si minus a times x of s. This is the equivalent of subtracting in matrix form, equals b u of s. Okay, that's good. Now I have a relationship between the state vector in Laplace domain and the input vector also in Laplace domain. But I need output. So let's take Laplace transform of this equation as well. So I have ys equals c x of s plus d u of s. I can calculate x of s from here and put it back in the other equation. So let me do that first. So from here, I can multiply both sides by si minus a inverse. Let me write it down. Si minus a inverse si minus a x of s equals b u of s. Oops, I'm missing what I multiplied. Equals si minus a inverse b u of s. And it is important to note here is that I'm imagining that si minus a is invertible. So this thing exists. And that is important because when you cannot define an inverse of that, for those s values that you cannot, interesting things happen. And we'll get to those later. Later in the next lecture, next few lectures. So these two cancel out. What I have is x of s equals si minus a inverse b u of s. And now I have x of s. I can substitute it here. So my y of s becomes c x of s, this whole thing, si minus a inverse b. I'm going to factor out one u of s plus d, all of it times u of s. So what I'm left with is y of s equals something multiplied by u of s. And remember, both of these y of s and u of s are vectors. This one, I think we use notation r. There are r y's and m u's. So this whole matrix is an r by m matrix. And this is what we call the transfer matrix, or G of S. It's an R by M matrix. It's called transfer matrix, and it includes as its elements individual transfer functions between different u's and y's. So G, for instance, G11 is transfer function between y1 and u1. G12 is y2 by u1. What? No, the other way around. y1 and u2. y1, u2 of s, and so on. So this transfer matrix contains all the information about individual transfer functions between different inputs and outputs of the system. And maybe it is useful to note that if I want any one of the y's, it is being affected. For instance, y1 is being affected by u1, u2, and so on. So any one of them, u1, is g11 u1 plus g12 u2 and so on. And that's how you can get the combined effect of all inputs on the output, and same for other y. Maybe there is not enough space to solve an example here, so let me have this in mind. Let me see if I'm missing anything else. No. Maybe now that I have space. So this G looks like something like that. Obviously G11, all of them, obviously G1M. They're all functions of S. They are transfer functions. GR1 of S, GRM of S. Okay, that's good. That's good use of the space. So let me clean the board and we come back with an example. Let's look at one example. So I have these state space equations, x dot 1 and x dot 2 equals a x plus bu, and I have two measurements coming out of the system, and I'm just directly reading from the two states. So this I is the identity matrix, 2 by 2 identity matrix of 1 0 0 1. So two input, two outputs. Let's find this transfer matrix. So let's start with this equation. So my G of S equals C Si minus A inverse times B plus D. Maybe let's look at this first. That I have Si minus A, so that is S0, 0S minus A. My A is this, minus 1, 6.5, 0. I think I took this example from the textbook, so I have no idea, or I don't remember why 6.5, but for the sake of it, just take it as some state space. And I want to eventually take inverse of that. So this is Si minus A. This one is S plus 1, 1 minus 6.5 and S. So when you want to take the inverse, it is 1 divided by the determinant of the function multiplied by something that you flip these two, and you flip the signs of these, if I recall correctly. So if you do that, actually I don't have it, but let's try it. So I'm going group. I don't know whether I reach the answer I have here, so let's see. So I'm looking for 1 over determinant. Determinant is S times S plus 1 minus, and it cancels with that, so plus 6.5 multiplied by S plus 1 and 6.5 minus 1. I think this was the inverse of a 2 by 2 matrix. So if I'm going to keep this. So I'll have S over S squared plus S plus 6.5 minus 1 over S squared plus S plus 6.5 over S squared plus S plus 6.5 and last one S plus 1 S squared plus S plus 6.5. This. Okay. So I calculated SI minus A. Now C is I, so let me write it down. C equals I. Well, actually, no, it's fine. So SC times whatever is whatever. So C, we don't need to worry about it. And what I have is this multiplied by B plus D, and my D is 0, so I don't need to worry about that one either. So this is plus 0U. U1, U2. So all I need to do is to multiply this by B. So now I don't need this. So my B is 1110, and I have S over S squared plus S squared plus S plus 6.5 minus 1 over S squared plus S plus 6.5 over S squared plus S plus 6.5. That's a 2. 6.5, and finally S plus 1 over S squared plus S plus 6.5. This multiplied by 1110, and what I have is S minus 1, S minus 1. So S this plus that. I'll have S minus 1 over S squared plus S plus 6.5. And then this times that, so I'll have S over S squared plus S plus 6.5. Now this plus this, so I have S plus 7.5 over S squared plus S plus 6.5. And last one, this and that, so I only have 6.5 over S squared plus S plus 6.5. And that is my transfer matrix G of S. So essentially, let me just double check that I have it correct. Yes. Good. I was not wrong. No. Okay. So this is G of S, and now my Y of S, let me write it as a vector. So Y1 of S, Y2 of S equals this G of S, U1, maybe capital, U1 of S, U2 of S. That's it. Okay, now I have the relationship between individual Y's and individual U's through this transfer matrix. So one thing, I was a little intentional in writing all of these many times. It would be boring, but there was a reason. That what I wanted to point out here is that this is same as 1 over derivative, 1 over determinant of the matrix. And it remains here all the way through. And this is not a coincidence that the characteristic equations for each of these transfer functions, essentially the denominator of each of these individual transfer functions, is the same, first of all, based from all of those, and also it is the same as the determinant of the A matrix. And remember that the characteristic equation and the poles of it, poles of a transfer function, defines very importantly defines the way a system behaves. And we'll expand on it more, that there is a one-to-one and very important relationship between the poles of a transfer function and when the determinant are 0, the values that make determinant equal 0. Those are the eigenvalues. We will get to those. But I wanted to be explicit in this example how they are related. Okay, that's good. That's good example. Let me again clean up the board, and we start thinking about going the other way around, going from transfer function to a state space representation. Spoiler alert, it's less straightforward. So let me clean up. Now it's time to go from transfer function to a state space. And unfortunately, this part is a little trickier because for a couple of reasons. The first one is that in general, a state space form of a dynamical system is not unique. So there is no unique way to go from a transfer function to a state space. In fact, there are, for any dynamical system, there are infinite number of ways you can represent that through a state space formulation. So that's one reason for complication. The other one is for the systems or for the situation when we have something called input derivatives. So it is very common that we have a transfer function that has some s terms in the numerator. So let's go with b, because we used to have b here. B m s m plus to b1s plus b naught divided by some an n plus plus a naught. So here we don't care about the denominator for now, but if, remember what this means. This equals y over u, and if I multiply this u by that, it means there are a bunch of derivatives of u showing up in the equations, the differential equations. And that is problematic because in many situations we have seen, we like to look at the impulse or step response, and if the input is, for instance, a step, its derivative would be infinite. So that can cause some complications. And to overcome that and write a meaningful state space formulation, we need to change the derivatives or do some tricks such that to make the system work. There are a few systematic ways, fortunately, there are systematic ways you can address that. And those are in the textbook. I'm not going to repeat it because it's a lengthy process, but systematic and can be done. So I want you to look at it. But let's for now look at just one example to see how things go. So imagine I have a transfer function g equals y of s over u of s. Again, I'm going rogue a little. This is not the same thing I have in my notes. I should have changed it, but it's fine. Let's pretend it's a simple transfer function without any s terms on top. So there's no derivative of u showing up in our equation. So I have 1 over s. Do I go cube or let's go with cube? S cube plus maybe b. Let's go with a yb. S cube plus as squared plus bs plus c. Let's go with that. So what I can do is to write my y of s equals u of s divided by this s cube plus as squared plus bs plus c. No, I don't want to do that. No, let's not do that. Let's do it this way. I'm sorry. This is what happens when you don't have good notes. So let's do this. S cube plus as squared plus bs plus c times y of s equals u of s. That's better. And then y of s cubed times y of s is the third derivative, y triple dot plus, I'm taking Laplace inverse, y triple dot plus a y double dot plus by dot plus cy equals u of t in time domain. So now I have this third order differential equation, and what I can do is start in a similar way we did it with the mechanical system. Let's call my x1, my first state, to be y, my x2 to be y dot, kind of the velocity, x3 be y double dot, my acceleration. And with this definition I can write, what is a good way to write it? Yeah, let's use dot notation. So x dot 1 equals y dot. So taking the derivative of that, y dot, and y dot is x2. X dot 2, taking the derivative of this, x dot 2 equals y double dot, and y double dot is this, which is x3. And x dot 3 equals y triple dot, which is minus a, y double dot, minus b y dot, minus c y, plus u. And y double dot is x3 minus a x3 minus b y dot is x2 minus cy is x1 plus u. All right. So now I have my equations. So again, this is the last time I'm writing it like this, but x dot 1 equals 0x1 plus 1x2 plus 0x3 plus 0u x dot 2. So whenever you are confused how to go from this form to matrix form, do this. So x dot 2 equals 0x1 plus 0x2 plus 1x3 plus 0u. Finally, x dot 3 equals minus c x1 minus b x2 minus a x3 plus 1u. So I have already constructed my A matrix. So my A is 0, 1, 0, 0, 0, 1, minus C, minus B, minus A. So let's put it this way, x dot 1, x dot 2, x dot 3 equals, this is my A, 0, 0, 1, no, 0, 1, 0. 0, 1, 0, 0, 0, 1, minus C, minus B, minus A, times x1, x2, x3, plus I only have one u, so it's going to be a column vector. My B is going to be 0, 0, 1 times u. And this is the state space form, so that is enough. But something I can do is take my y, my output measurements, to kind of have the same thing, to be just a readout. Let me write it down. Readout of, I hope you can see down here. I think you can. Zero, 1 of x1, x2, and x3. Well, actually, no. Let's go with this. Let's do that. That keep y. I want y the same thing as I had here. So that is only x1. So let's not do that. I don't want all of them. I only want x1. So it's going to be this 1, 0, 0. This is better. Plus 0 u. So now I constructed the state space equivalent of the system described by this transfer function, and it is this. So this is kind of a how would you say it, ad hoc method that you have to use a little experience and a little brain power to know which states to choose such that things work out. In the cases that we don't have a state derivative, so the numerator of the transfer function is 1, it is easy. You can take your states to be consecutive derivatives of your output measurement until how many you need to get to the derivative, the final derivative you need, and work out fairly systematically what are the state equations, and then construct your A, B, C, D matrices. When you have these state input derivatives, when the numerator of a transfer function is not only a scalar constant value, there are s, things become a little messy. You have to be careful how you choose your derivatives. There are guidelines, not guidelines, systematic methods that can tell us how to construct these state spaces to reach a certain property that we like. And it is important to note, again, I'm reiterating this, that this choice is not unique. And any of these systematic methods that I mentioned, they are in the textbook. What do you want to say? There are different ways or different methods to construct this, and the end results would be different. So you would end up with a state space form that is called control canonical form. You may end up with another thing called observable canonical form, or Jordan canonical form, or there are many different ways and forms you like to have your state space in. For instance, the one that is called controllable canonical form will give you a state space equation that, as the name suggests, is a controllable system. Whatever that means, we don't worry about that too much. And yes, yeah, that's all I have. Let me see. And the last bit, that maybe this is enough. So I have mentioned all of these different state space forms, that all of them are valid. And I mentioned it up here that the choice of a state space is not unique. There are an infinite ways. And you can go from one representation in the state space form to an alternative one. And to see that, let's again look at this. X dot equals ax plus bu, and y equals cx plus du. So let me change my variable. So instead of working with state variables that are named x, let's change variable and use with something called z. And here my z, I can define those as a linear combination. Let me define my z through this as a matrix P, which is invertible. That is, the inverse exists. And multiply that by x. So if P is a matrix, or P inverse is a matrix, you multiply by the vector x, you get another vector, possibly with a different dimensions, called z. Or x equals pz. This is another way you can write it. Now substituting this into that equation. So P is a constant matrix, just a bunch of numbers, and P inverse is also a bunch of numbers. So if I let's work with that, take derivative of it. So x dot becomes pz dot, pz dot equals ax, x is pz, plus bu, we leave it as is, and y is cx, cx is pz, plus du. Now again, remember we said P inverse exists, so P is an invertible matrix. I can multiply that by P inverse, so Z dot equals P inverse A P Z plus B P inverse B U. And this one I keep the second one as is, so CP Z plus du. And now essentially what I have done is construct a different state space equation where I have different A, B, C, and well, this one remains the same. Different A, B, C matrices. So as long as I can find a P that is invertible. I can transform my state space from one form to any number of infinitely possible alternative state spaces that are all of them valid. And sometimes we want to have a certain property of our state space form. For instance, it sometimes is useful to have equations that are something called decoupled, meaning that x1 is only a function of x1, x2 is only a function of x2, so you want to have only elements at the diagonal, and with some choice of p, it is possible to do that given certain limitations, to decouple the equations. So let me see. So that's all I have for now. So we have introduced the state space. We have seen how we can go back and forth between the state space and transfer function. And again, I reiterate, there are methods in the textbook to systematically tackle this problem, and I want you to look at them. And in the next lecture, we will start to use these state space form to analyze the system, and we'll see how it can give us, in the same kind of framework, a very nice visual representation of the system. We can do stability analysis, we can do frequency analysis, and what else? Is there anything else you're doing? No, I think that's all the three things we will be using in this notation. So study, and I'll see you next time.